Okay, so before we get started, any questions on homework or anything else?
So I have a question.
Okay.
The theorem one that we did, is it like remember the first few weeks when we did a Python function about the digital, the M covering T or whatever? Is that what theorem one is like?
Um.
It was question 4 in test 1.
Oh, yeah, that was very much the same kind of proof
Oh, okay. So
where
basically, so
show
can
that
you?
if you list them all out, there you can't. You say you list them all out, but then there's one that's missing.
Oh, okay, I see. Thank you.
Mm-hmm. In fact, I'm pretty sure that's what we did on Monday. But the first theorem one should still have everything there, so there's not much for you to do. Theorem 2 has like half of it, and then theorem 3 is pretty much blank. All right, so that's homework that's due Friday, and those three theorems being true is if you haven't finished the homework, then just take it on faith that they're all correct. And once you get done with the homework, you'll see why. So going on the assumption that they're all correct, we're going to look at what we have here. So what we're going to do is we're going to make a Python program that should not be able to be made. So we're going to implement a function that can't be implemented. Now, how we know that is the case is because I'm going to cleverly construct this program so that a bunch of stuff relies on one function. And this one function is going to be un-implementable because of the things we just proved. I believe theorem 3 was saying that there is an infinite bit sequence that no Python program can display or generate, something along those lines. We're going to do something very close to that. In fact, it's equivalent. So the idea is as follows. Let IBS be the set of all infinite bit strings, that is functions from the positive natural numbers to 0, 1. So as I'll give a quick example. Here is a function from the integers, positive integers, to 0, 1. There. So that's going to be the infinite bit sequence. I guess we start at 1, don't we? This is going to be the infinite bit sequence of 1, 0, 0, 0, 0, 0, forever and ever and ever. So that's 1. In the, I believe, theorem 1, we showed that given any function f from IBS, we can construct an infinite bit string that's not in the range of f. So that means we couldn't possibly list all of the infinite bit sequences, showing that it's uncountable. There was no surjection from in to those bit sequences, meaning that You couldn't map to everything in the set of infinite bit sequences. There's just too many of them. So to come up with a concrete example of an uncomputable function, sorry, kind of weird to say, let f be a particular function that maps the positive integers onto the countable set of all functions definable in Python. And then basically repeat the steps of the proof for this function f. This defines a concrete function that is not in the range of f, which is to say a function that cannot be implemented in Python. That was theorem 3. But that was just the proof that it can't be done, or that there exists a function. You list out all the functions definable in Python, and you have them all, but then here's one that's not there. Same style of proof. But now we're actually going to write some code to do it. Let's change things a little bit. So we're going to have this function ID from the positive integers to 0, 1, and it's going to look like this. We're going to have this string. I'm just going to call it string for now. It's going to be an infinite sequence of all finite strings of ASCII codes. So what's a finite string of an ASCII code? Well, there's one. There's another one. There's another one. So that's one sequence. It's finite. How do I know? Well, it has a length. It's not infinite. There's another one, and there's another one, and an infinite sequence of these is to have an infinite number of these. Any ASCII code I wish. Now I'm going to have a particular way of listing these out, but that's just saying what a infinite sequence of finite strings would look like. So in particular, let it be the sequence consisting of all strings of length 0 in lexicographic order, followed by strings of length 1, so on and so forth. So what do I mean by lexicographic order? Does anybody know what that means? Not sure. Okay. Well, can somebody give me a string of length 0? And let's just consider our alphabet for now to be digits 0 through 9. Can someone give me a string of length 0 of those using that alphabet? That's right. Are there any other ones? I lost the lid. It's way down there. Okay. All right. That's the only string of length 0 given our alphabet. In fact, it's the only string of length 0 given any alphabet, unless you do something really weird. All right. Can someone give me a string of length 1 using our alphabet? 1. Okay. How about another one? I'm going to get rid of the quotes. 9. There's one. What's another one? No, that would be a string of length 0. We can't use that one. We already used that. Okay, 0. Give me one more. Actually, this will be fine. We'll go with that. So let's get 4 strings of length 2 using our alphabet. And trailing zeros are fine. So someone give me some strings of length 2. 23, 45. You both said 45. That's kind of weird. 69, 87. Okay. Now, lexicographic order. What is lexicographic order? Well, it's whatever I define it to be. And what I mean by that is I'm going to give a ordering of all the symbols in our alphabet. And whatever that ordering is going to define what lexicographic order is. So this in lexicographic order is 0, 1, 5, 9. 0 comes before 1 in the lexicograph. 1 comes before 5. 5 comes before 9. Now this one, we apply the same thing, but let's change this one to 67. We do the same thing, but we apply it to the most significant digit and onward if we need to. So what's the first on the most significant digit? It's 23. Do we have any ties? No, we don't. All right. Well, the next one is 45. We don't have any ties. The next one is 69 and 67. We have a tie here because they both have a 6. So we move on to the next most significant digit, and we see that 67 comes before 69. So that is the order they'll be in. That's lexicographical order. Lexicographic order. So any questions on that? Don't see any questions. Okay. I'm cool with that. All right. So any questions on what, and I expect there's going to be a lot, any questions on what the string sequence is? It is a sequence consisting of all strings of length 0, followed by strings of length 1, so on and so forth. So is anybody unclear as to what string is? First thing I'll ask is what kind of thing is it? It's on the screen. You can read it off if you want, but I want to make sure that people don't have any misconceptions as to what the type of it is. Is it an integer? Is it a string? Is it a character? Is it a... Okay, well, that's a bit more than I was asking, but that's correct. It is a sequence. It's a sequence of strings, and it's an infinite sequence of strings. It's a sequence of characters. I wouldn't say that. It's a sequence of strings. That's I would pretty much say that's not right because 0159 is not a character, and that is an element of our sequence. So it is a sequence. That is the big thing to remember. It is a sequence of strings, and moreover, it is an infinite sequence of strings. Okay, so question. So is a finite sequence? I don't follow what that question is asking. If you can think about it a little more, I'll try to answer it. Some strings define Python functions and some don't. That's a interesting statement, isn't it? Let me go yank one from my program. I've already written this, by the way. The task you're all going to be given is not to write this. I've already written it for you. It's already here. You can copy it. The task is going to be analyzing this code and telling me what's wrong with it. Juanita, do you understand why I don't understand your question? Okay, if you want me to try to answer it, I can, but I need some refinement. Okay, so is this string, does this string define a Python function? Does that? Okay, that happens a lot. That's a good thing. Does this string define a Python function? The string consisting of the ASCII code 9. No, it doesn't. What about this one? I get my syntaxes mixed up sometimes. What about that? Should work. Does that string define a Python function? Yep, it's not a trick question. If I made a syntax error, so be it. But yeah, that string defines a Python function. That one doesn't. So the point I'm trying to make here is exactly what I said in the bullet. Some strings define a Python function and some don't. So if I am, and if I were to do this, I'm pretty sure. I'm pretty sure this gets the point across. If I were to list out all the strings I can possibly make, all of them forever and ever, I start out with length 0, and I go to length 1, I go to length 2, and let's see, what's the length of this? 1, 2, 3, 4, 5, 6, 7, 8, 11, 12, 13, 14, 15, 16, 17, 18. So we're on strings of length 18. If I list out every string that can exist of length 18, hey, I've got at least one in that big list that defines Python function. There's not going to be an infinite number of them. How do I know that? Is because for each space in my 18 characters, there are only so many, the 256 characters I could put there. No, it's 128. There's only 128 characters I can put there, and there's what, I said 18 spots. That's a huge number. It's probably more than the number of particles in the universe. It's 18 to the 128th power. Yeah, that's way more. It's a number so huge that we can't even comprehend it. Just consider it large. Point is, it's not infinite. And if I jumble the letters up long enough, have monkeys on a typewriter, eventually you'll get Shakespeare. But if I jumble the letters up long enough, eventually I'll get this string. I've got 3 strings here. So 2 questions. Is this put question 1, even though it's more of I guess you could call it a question. Put this into lexicographical order. And question 2, which of these 3 lines here define Python functions and which ones don't? So I'll let this one be number 1, and this one be number 2, and this one be number 3. Now, what's the lexicographical order that these should be in? I wrote these intentionally carefully so that this shouldn't be very difficult to answer. 1, 3, 2. That's correct, because they're all the same character up till the very last one, and 1 comes before characters. So numbers, at least I think. If not, it's fine. You got the point of the exercise. I actually don't know. Do numbers or characters come first? Let's assume numbers come first. It doesn't matter. So in that case, it would be 1 and then 3 and then 2 because n comes before x. So that's good job. Now, which ones of these? Yep, that's exactly the point. Which ones of these define a Python function and which ones don't? So you're saying that number 2, does not define a Python function. 1 and 3 do. Okay. So this is all to illustrate the point that some strings define Python functions and some don't. And I'm not actually listing, when I make string, I'm not actually listing out Python functions. I am listing out strings. I am being the monkey on the typewriter. And the point is, if I keep doing it for a long enough time, eventually I'm going to give you a Python function. Okay. Now, let us define the infinite binary matrix A, whose I, jth element. We've done this a lot, so I'm not going to list it out like I usually do because we've done it so often. If somebody has questions on it, feel free to ask, and I'll try my best to answer them. So the I, jth element for I and j being a positive integer is going to be 1 if the ith string in our sequence defines a Python function that maps j to 1. And it's going to be 0 if it defines a Python function that maps j to 0. It's going to be 0 otherwise. That is, if the string does not define a Python function, or the function defined by the string is not defined at j, or the function defined does not map j to a bit. So what does that mean? Well, let's say I'm listing out all my functions as I was before. So I don't know what I is going to be in this case. I need my pen. And let's use red. Let's say that, I don't know, we're 403 lines down. There's no way that's true because this is going to be, we're so deep in here that the mind boggles. But let's just pretend it's 403. This is line 403, this is line 404, this is line 405 in our listing of strings. So the question here for this line is, what is I and what is j? So for I here, what's our I? We're trying to fill out our matrix. Got 1, 2, so forth, 403. It's going to be a terrible line. 1, 2, 3. Yeah, that's fine. I was intending for it to be 403, but that's fine. You got the point. For blah 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 blah. Okay, so we're at line 403. You say 404. That wasn't a joke. It wasn't supposed to be a line not found joke, but I'll take it. I'll take it when I can get it. All right, so we're at I equals 403. Now, what's our j for our matrix? Yes, good. You got that quicker than I thought you would. J is not just any number. It's going to be all of them. It's going to be 1, 2, 3, 4, 5, 6, 7, forever and ever and ever. All right. So what is the value in slot I equals 403, J equals 1? Can anybody give me that? D. Interesting to say because I see what you're trying to do. You're trying to get the first character. That's not how this matrix is going to be filled out. This matrix is going to be filled out according to these rules right here. So it's only ever going to be a 1 or a 0. But that was not a bad shot. So it's going to be a 1 if our ith function maps the j that we're taking to 1, and it's going to be 0 if it maps it to 0 or 0 otherwise. Okay, so what's my j right now? It's going to be 1. What does the function at line 403 map j to? Well, it says define f then as return 1. So it maps 1 to 1. So according to those rules, what should the entry into A be? Brandon says 1. That's correct. Why is that correct? Because it string at I, which is string 403, is this right here. F of 1 returns 1. So it maps j to 1. We enter 1 in the matrix. What does this function map j equals 2 to? To 0? Interesting. Define f of 2, return 1. Why does that map it to 0? We haven't moved off of 403 yet. We're just going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what's if I were to input 1 to this function, it's going to return 1. So I put a 1 here. If I input 2 to this function, what does it return? 1. That's correct. What about 3? This function is always going to return a 1. So the entry for line 403 looks like that. That is correct. And I am not that smart. I didn't make it this way to show that intentionally. I just got lucky. Okay. So what about line 404? What's the entry for this line look like? What's the function I'm going to try to plug things into? Brandon, you're correct as what it's going to look like, but can someone tell me what the function that, or the string that we're hoping is a function, which one is that going to be? No, it should be number 2. Oh, I guess you're correct because we've swapped them around. We've listed them in lexicographical order. So yeah, that's right. So if that's the case, let's look at 405 because I'm less interested. Well, that's fine. So let's go with 404. 404 is going to be number 3 here. It's going to be take in whatever your input is and return it. So what's the line going to look like? Well, it's going to look like 1 because take 1, return 1. And then everything else is going to be 0 forever and ever and ever. Okay, what's 405 going to look like? That is define f of n as return x. So question 1, is that a valid function? Yes, it's going to be all zeros. It's not a valid function, and so we've got a line for that in our rules over here. It says 0 otherwise. If the function is it's not a defined function, so it's going to be zeros. So this is going to be 1 1 1 1 1, and then 1 0 0 0 0 0, and then just 0 0 0. Okay. Does anybody have any questions on what the matrix A should look like? Cool. All right, so we've done the thing we always do. Every function from the positive integers to a infinite bit sequence definable in Python is now a row here. Now that step's very important. Does everybody understand that I've listed out every string that can exist? of ASCII sequences. Some of those make Python functions and some don't. But since I've listed them all out, I've painstakingly listed them all out, this matrix is so large that you can't even comprehend how large it is. But if you take the lines of this matrix that refer to a function in Python, I've got them all. Can anyone give me a sequence, an infinite bit sequence, that should be in this matrix but isn't? What would it mean if there were a sequence that should be in this list but is not there? It would mean a lot of things, but you could say any of them and they pretty much mean the same thing. This is the same thing we've done for question 4 on the first test and the 3 theorems we just proved. That is one of the things. It would mean the string is not covered in the matrix. But what would that... trying to get you guys to say some of the consequences of that. Like, I'm not just... well, 0, 1, 1, 1, 1, 1, 1 should be in here somewhere. I just haven't listed them all out. That is absolutely correct. We want to take the diagonal. So whatever the first line is, take the first digit. Could be 1, could be 0, who knows. I'm going to define some function. I'm going to say, it's the same one we always do. I'm going to say d of n is 1. Well, actually, I can just do this. 1 minus a in n. That should work. I'm saying look at the first row, first character. Take 1 minus whatever it is. Second row, second character, so on and so forth. So I'm going to end up with a sequence that is different from each sequence in this matrix by at least 1 digit, meaning it's not there. So yeah, that's what we've made. So if every sequence in here represents a Python function and a specific Python function from the positive integers to 0, 1, and I have them all, but there's one that's not there. So that means there's a Python function that's not in the listing of all Python functions. So this means a couple things. They're actually the same thing, but can anybody tell me some of the consequences of this? The consequence of we can't possibly list out all the Python functions. We're missing one. Take too long? It would take too long for you to explain the consequences, or at least one consequence of that? Not quite sure what you mean. So the reason I'm trying to get you guys to say one of the consequences of this is to get across the point that I'm not just having you do these strange proofs just so you can. I generally don't give you guys something to do unless there's a meaning to it. No, what is the consequence of I've listed everything out and you pointed something out that's missing? Meaning I can't list them all out. There's too many. What was the neat fact of doing this with the real numbers? Because really what this is saying is that there's no surjection from the natural numbers to Python functions that map integers to 0, 1. We could tell if it is countable or uncountable. Yes, that is true. Then would it be saying the string doesn't define the Python function? I'm not quite sure what you mean there. So I'm going to go back through this a little bit so that you're less confused. So what I've listed is every string I can think of from the ASCII code. I'm going to start with length 0. There's only one. I'm going to go to length 1, and there's 127. And then I'm going to go length 2, and we're starting to get into a lot here. It's what, 2 to the 128th power? I don't know what that number is. Maybe 256, it goes that way. But then length 3, and then length 4, and so on and so forth, forever and ever, because my listing is infinite, but each element in the listing is finite. Now, some of those listings, each entry is a string. It's a finite string. Some of those strings define Python functions, and some of them don't. So now what I'm going to do is I'm going to go through each string I just listed. If it doesn't define a Python function, I'm just going to fill out the entire row with zeros. If it does define a Python function, I'm going to take its input, give it a 1, give it a 2, give it a 3, give it a 4, and see what it gives me back. If it gives me back a 1, I'm going to put a 1 in the matrix. If it gives me back a 0 or something else, I'm going to put a 0 in the matrix. So now I have this big matrix, and this matrix gives me a row for every line in my listing. And since my listing is infinite and it's everything that I could ever write in a Python interpreter, I know that I have every function that I could ever implement in Python. How do I know that? Because every program is finite. Every character you enter is only a couple you can do, 128. So everything you can think of writing, I have it in here somewhere. And so since I've listed everything out and shown that there's one I'm missing by taking the inverted diagonal, what does that mean? Well, Monica pointed out we could tell if it's countable or uncountable. Yes, that is correct. This is showing that it is not countable. It's showing that no matter what we do, we're always going to be missing one. So that's strange. So if we're always going to be missing one when we try to implement this function, and the function is only complete if we get them all, what does that mean about the function? So if the function is done when I list out all the strings, but the number of strings is uncountable, so let me put it this way. The function is done when I count a list of uncountable things. What does that mean about the function? It's actually on the screen, but it's fine. The function will never be done. That's a good way. That's fine. I'll accept that. The function can't be done is what I'm trying to get you guys to see. If I say I want you to implement a function that counts an uncountable list, what would you say back to me? You'd be like, I can't do that. No one can do that. It's impossible. It's actually the point, the title of the lecture, an un-implementable function. This function, ID, does that very smart. It correlates to the halting problem. Yes, very much. So, the entire last 40 minutes, and again, I'm happy to take all the time I need because it doesn't do me any good so sneak preview, your homework is going to be, I've already implemented this. I've implemented a function that can't be implemented. So something has to be wrong with it. Homework's going to be figuring out what's wrong with it. It wouldn't do me any good to just say that and then say goodbye and go, I don't know, mow the lawn. Actually, I think it rained, so that would be a bad idea. Anyway, doesn't do me any good to do that. I'll take as much time as it needs within reason for you to understand what I'm trying to give you before I give it to you. So I've painstakingly listed out why this program should not be able to be made. Before I move on to actually implementing it, does anybody have any questions as to why, when I say you can't, this is an impossible program, you should be able to point at this little proof I did here and say, yeah, that's why. Even if you don't understand every step all the way through, you should be, if I were to ask you on the exam, tell me why this function can't be implemented, you should be able to do it. So does anybody have a question on this part before I erase all this stuff? Now you could probably pretty much guess this has something to do with the halting problem because I have this one up right here. But that's fine. All right, I don't see any questions, so I'm going to clear all that and we're going to. All right, so we have this function that can't be done. So what happens if I try to do it? If it can't be done and I try to do it, something weird's going to happen. What's that going to be? So in order to make this a little easier to look at, I'm going to define this function. It is enum ASCII lists. So does everybody understand what it means to enumerate something? To enumerate, that's the best, simplest definition I can give you. You list something out in an order. So enumerate the integers. Okay, I'm going to do the positive ones first. 0, 1, 2, 3, 4, 5, 6, 7, blah, 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 blah. And eventually, I'll get to the negative one. Actually, no, I won't. So 0, 1, -1, 2, -2, 3, -3. I'm enumerating out the integers. Enumerate the foods in my fridge. Okay, I've got some avocados in there, and I've got a whole bunch of pickles, and so on and so forth. Enumerate the students in the class. Okay, well, there are 33 of you right now, so I guess 32. Pick an order and list them all out. That is what it means to enumerate. So, to enumerate, aren't enumerations not able to be changed? Once you pick an order, yes. But I can pick whichever order I want. Usually it's not a good idea to make weird orderings, though. All right, so we're going to define this enum ASCII lists. It's going to be the sequence of lists of ASCII codes consisting of all links of list 0 in lexicographical order, and then lists of length 1 in lexicographical order, so on and so forth. Same thing we did above. Here is some sample inputs of what this is going to look like. So the first output for my function, I wonder. Hey, that's cool. 1 second. Nope, not that one. That one. Can everybody see my Python window now? Okay. Let's see. I always type this wrong and I don't know why. Oh, I didn't run the program. I am smart. Okay. So if I'm going to list out some inputs and outputs, here's a table of what it would look like. Now, I am quite sure that if I were to ask some of you what the 131st output of this would look like, you would be a little bit confused. So let's take some time to go over it a little bit. So I'm going to list out all the sequence of ASCII codes of length 0. I'm going to order them. At length 1, I'm going to order them. Length 2, I'm going to order them, so on and so forth. That's what this function does. So that table kind of looks like this. So can someone tell me why when I get to 129, it is that, and when I get to 130, it is that? Because this is, it's, why is it putting a 0 after a 127? Shouldn't a 0 come before a 127? That's kind of weird. Would it be counting by bits? Are you asking the question? Are you trying to point out that the output for this one has one element and the output for 2 has 2 elements? Another person said 128 minus 1. That has something to do with what we're talking about. And I was going to get to that in a second because 120 is the number of characters in ASCII. Everything you guys just said is correct. I think what all of you are trying to say is there are 128 entries. Well, let me put it this way. There are 128 outputs from my function that have length 1. Can anybody tell me how many outputs from my function have length 0? This is what Brandon was pointing out. There's 1. And so when I input 1, the very first entry in my table here is the only enumeration of length 0. Okay. So now we're on to enumerations of length 1. Well, I won't say that. I'll just say outputs from now on. We're going to move on to the outputs of length 1. All right. So the first one, oops, I wish there was an up. The first one is that. The second one is that. And I'm going to keep listing these out. And the last one of length 1 is that. So there's 128 outputs of length 1. And they give me 0, 1, 2, 3, forever and ever, all, well, not forever and ever, up until 127. Okay. So now I'm going to move on to length 2. 130. This is the first output of length 2. Now, how many outputs of length 2 are there? Well, there's what? 16,513 minus 129. So that's fine. But let's look at it this way. How many outputs do I need to go through? Well, actually, how many inputs do I need to go through until so I'm going to get outputs that look like this. X, or some X is some number between 0 and 127. How many do I need to go through before this first digit changes to a 1? Can anybody tell me what that would be? Anybody tell me the input to where I get a 1 in that first character, first number? 128? No, that's not quite right. Oh, you're saying how many do I need to go through? Okay. So if that's how many I need to go through, and this one gives me the first one, what should that number be? Should it be 258? Yep, sure is. Okay, so now I know how to go through all the ones with a 0 in the first one, and it's going to list out stuff here. So like 257 is going to give me 0, 127. And I can get 0, 0, 0, 1, 0, 2, 0, 3, all the way to 127. And now I get 1, 0. Okay. How many different numbers can I have in the first slot? $127. Actually, I think there's 128 because you're counting 0, 2. So that means for anything in 0 to 127 and anything in 0 to 127, there is an entry in my table here that starts at line 130 and goes all the way to line 16,513. So after that, it gets really big. So what's the output for 16,512? Well, it's that one. 16,514. What's this output going to be? It's actually on the screen. It's fine. But what's the output of this going to be? 0, 0, 0. Well, that's weird. I thought we were only listing things out of length 2. Why did you give me something of length 3? So 16,513 is going to be 127, 127. 127, comma 127. Is there a 127, comma 128? No, because it's as if asking if you're going 0 through 9, and I'm asking you to list out all the digits, and you give me 10. Well, 10's not a digit. It's a 1 and a 0. It's not a digit. So the next element after 127, comma 127 would be, okay, move on to the next digit. So 0, 0, 0. Now this one, let me think. What's the calculator? Let's see. If anyone can tell me what 127 cubed is before I can move my calculator to a good spot. 127. To the third power is a big number. That's right. That's the correct number. So this should give us 4 zeros. I might be off by one. 2,048,333. 383. 2,048,383. It's going to be more than that then. I missed something. Oh, yeah, because I have to add that, don't I? Plus 16,512. So that's, yep, that looks more like a number we're used to. 2,064,895. I don't think commas work, do they? That moves on to the next one. It's even bigger than we thought. So it's not the cubed, is it? It's 3 to that. That's nuts. So 3 to the 128. Yep, that number is too big. That number is way too big. All right, I'll let you give me one more funny input here before we move on to something. Can I explain why there are 3 outputs? Do you mean why there are 3 digits? Somebody think of a big number, and I'll put it in here while I answer this question. Are you asking why there's 3 digits? It's because I'm listing everything. Okay, I'm listing all sequences of digits, or not digits, integers 0 through 127. I'm going to start out. So my alphabet, I wonder if I can still do this with my actual screen share. My alphabet is 0 through 127. Okay, so I can make any character in my string can be 0 through 127. So can you give me a string from that alphabet of length 0? There you go. Good job. How many of those are there? How many strings of length, how many unique strings of length 0 are there using this alphabet? There's only one. All right. Can you think of a string in this alphabet of length 1? All right, there's one. Can you give me another one? 8. Okay. So how many unique strings of length 1 are there in this with this alphabet? Yep, there are 127. What comes next after strings of length 1? Strings of length 2. Okay. Can you give me one? That's of length 1. 65 is a character in our alphabet. A character in our alphabet. And you only gave me one character. I need 2. Because 65 is, okay, 6 and 5. That's a good one. 6, 5. All right. There's one. Can you give me another one? 8 and 3. All right. So 2 questions. One is this in correct lexicographical order? Lexicographic order. You can't see my annotation? That would be very strange that one person can't see it. Oh, yeah. It's on the right-hand side of the screen because my left-hand side's filled up by the Python's thing. Anyway, so this is in correct lexicographic order. So the next thing is, how many strings of length 2 are there? Well, there's 127 slots here, and there's 127 slots here. So when you get to 16,513, we've gotten to 127, 127. All right, what's the next one? We've listed all the strings of length 0. We've listed all the strings of length 1. We listed all the strings of length 2. What's next? It's not strings, they're sequences. Okay, we're moving on to a sequence of length 3. What's the first sequence of length 3? No. Empty is a sequence of length 0. Empty is not a character in our sigma. It is 0, 0, 0. That is the first sequence of length 3. And we're going to go on 0, 0, 1, 0, 0, 2, 0, 0, 3. And eventually, and this is kind of the thing I've been waiting for, is 0, 0, 0, 0. We're going to get there eventually. Did somebody think of a big number? Yes, you did. Okay, thank you. Would you give it to me, please? All right, let's try it. Hey, at least we got 4 digits. Let's just add zeros to it, see what happens. Well, thank you. Thank you, Python. Hey, there's 5. There's 1, 2, 3, 4. No, we're still in the 5 land. All right, you get the point. This is essentially, so we can count in a lot of ways. We can count in binary, so 0, and then 1, and then 1, 0, and then 1, 1, and then 1, 0, 0, and then 1, 0, 1. Or we can count in decimal the way we usually do. You just go 1, then 2, then 3, and then you get to 9, and now we go to 10, and then 11, and then 19, and then you go to 20. We're counting in base 128 is what we're essentially doing. We're going to list them all out. Okay. So I have a, obviously, program that does just that. Lists everything out. But the program I have here, this is the code I have in my program, by the way. I'm going to share it with you. The comments are in it also. Here, I'll just show you. Remember what the impossible function was? Remember what I named it? ID, correct. No, that and ASCII is just the one I'm using to get there. ID is the impossible function. This is the one that I can't actually. ID is not the impossible function. I'm not going to tell you what the impossible function is because that gives away the homework. Something in this program should not be able to be made, and that's what the homework is. But here's the homework with a bunch of comments. There should be no question as to what each line or what each function does. That shouldn't be. I've constructed this program with so many comments that you should be able to figure out what every function does. The point of the exercise is to be able to look at this program as a whole and be like, wait a minute, this shouldn't be able to be done. What did I mess up? So I've implemented, so I take back what I said about ID being the impossible thing. The entire program is what shouldn't be able to be done. We've done something that I proved to be undoable. Right here, I said it can't be done, and I didn't mess anything up. So I've done something that should not be able to be done. But what how is that possible? I don't know. So is it just because it's in Python? Would it be better if I did it in C++ or something? So here's the homework. You need to implement these functions. I'm going to give you the code. So it's not that you're going to have to write that much. You just need to tell me what's wrong with this code. Why is it not implementing what we said we were going to? So that's the homework. And yes, the eventual answer is I'm trying to solve a halting problem. You can't do it. So don't try to get smart. Well, do, but not in that way. All right. Any questions on any of that? I'll bring up the code if you want. I can't fit it all on one screen though. Any questions as to what the homework assignment is? Okay, I'm going to end the recording there since we're over time and let it render.